Hi there. So now that we have the basics of vectors down, what we want to do in this video is just go over some more detailed topics with them. And there's going to be quite a bit of vocabulary to keep up with. And just want to show you a few things that we can do with vectors. Okay, the first thing I want to mention is what's called the zero vector. And we'll usually denote that zero. Again, there's different notations for vectors, however you want to denote them. And then just be aware in books, they'll use the boldface zero like that. Okay, but what this is, it's a vector with magnitude zero or length zero. That makes sense. But also, since it has no magnitude, this is the only vector that has no definite direction. Okay, but it's an important vector, and I'll show you why in just a moment. But in coordinates, you can probably guess. If you want to specify coordinates for the zero vector, that would just be 0, comma 0. All right, and so this is an important vector because we could have a situation where we actually subtract a vector from itself like that, and so make sure you realize that that would end up being the zero vector. Okay, and just to give you a little bit of preview, remember forces are vectors, and so if there's forces acting on an object, but the object's not accelerating, i.e. it's not moving at all, then that's said to be an equilibrium. And what that means is that the sum of the forces is equal to the zero vector. So people that end up doing statics problems especially end up dealing with the zero vector quite a bit. Okay, and then the next term to talk about are what's called equivalent vectors. Okay, and what equivalent vectors are, they have the same magnitude and direction. Okay, or the same length and direction if you want to think about it that way. Okay, like that. And so, in terms of coordinates, whenever we look at their coordinates, they'll be the same or equal. Okay, and then I'll point out the reason that we use the different vocabulary that we say equivalent, because here's two equivalent vectors right here that I could have this vector right here, and then I could go and have another vector. It's technically located somewhere else, so it could be over here. Okay, but it does have the same magnitude and direction, and so if we give them names, u and v, like that, we would say that u is equal to v. Okay, and we'll do that, but we just use that different notation because in practical situations, those vectors could be acting at different places. So they're essentially the same vector, but they might be located at different locations. All right, and then one notion that gets a little bit confusing to students is the idea of what are called parallel vectors, because we have the idea about what a parallel line is. All right, and so we would probably predict that this vector and this vector are parallel if I drew that a little bit better, right? And so those are parallel, but what's the difference in them? They have different sizes, right? And if you think about it, what changes the size of a vector, the length of the vector, but not the direction, and that's just a scalar multiple. So this vector right here is a scalar multiple of this vector right here. Okay, and so that's how we define parallel vectors. It's slightly different than you would think of with lines. And so two vectors, u and v, are going to be parallel if u is equal to some scalar multiple of v. Okay, and then if that's the case too, then it would go the other way too. This would be another constant. It would actually be 1 over c, but I'll just give it a different name, k times u, like that. All right, and so that's all we mean by parallel vectors. Now make sure you realize, remember, scalars can be negative. So this vector is parallel to this vector, okay, is parallel to this vector, but it's also parallel to this vector. It's just there your c is negative, okay, and same thing is parallel to that vector as well, okay. And so if you end up having a situation, say I have a vector like 4, 8, okay, notice that I could factor out a 4 from that. I get 2, 1, 1, 2, sorry. I'm not being careful there. So I get 1, 2, right? Like that. And so what that's saying is that the vector 4, 8 is parallel to the vector 1, 2. Okay, because 4, 8 is just a scalar multiple of 1, 2. So that's all we mean. And a lot of times, in some cases with vectors, we're not so interested in the size, we're just interested in the which direction it's pointing. So we might start out working with this vector, but if we don't really care about the size, since it's parallel to this vector, we might just use this simpler vector instead. And then very important in working with vectors, especially for the mathematical, as for mathematical tools. And like I said, sometimes we only want the direction of a vector. We don't really care so much about the length. And so what we'll use is what are called unit vectors, or a unit vector. Okay, and what a unit vector is, it's just a vector of length 1. Okay, like that. All right. And so it's kind of hard to find vectors of a given length. I'll show you how to do it in a minute. It's not hard, I didn't mean to say that, but just to think of vectors that have length 1. Okay, but hopefully you see that these vectors those are all basic unit vectors. Okay, like that. And then, there's also some other ones. And so the square root of 2 over 2, comma, the square root of 2 over 2. You could verify that that's a unit vector. And it doesn't matter about the signs. Remember, whenever we compute the length, we square each of the coordinates, okay? If you want to see that, let's compute the length of that vector right there. Then I would do the square root of the first component squared plus the square root of the second component squared, not plus the square root, plus the second component squared. Take the square root of the whole thing, okay? Just remember we're squaring a fraction, so, if I got square root of 2 over 2 times itself, like that, we multiply fractions straight across. So square root of 2 times the square root of 2 is just 2, but 2 times 2 is 4, okay? And then same thing over here, 2 over 4, like that, and then we have a common denominator, so we just add in the numerator. We get the square root of 4 over 4. That's the square root of 1, which is 1, okay? And so what we just showed there is square root of 2 over 2, comma square root over 2 over 2 is a unit vector, okay? Like that. All right, and then again, if you're having trouble seeing that, remember these signs can be anything they want, because why? If I had a negative here, it would be right there inside of the square. After I squared it, it would go away. All right, now this is going to be just a basic problem for now, but it's going to be a tool we use later too. All right, and so say I'm given some vector v, and what I want to find is a unit vector, so a vector of length 1, in the same direction as v. Okay, you might want to, after I draw this and show you what's going on, you might want to think about how you would do that. So, you might want to do that. So say this is v, and say right now its length is bigger than 1. So I want this vector right here that's in the same direction as v, but I want this length right here to be 1. Okay, like that. And so I didn't draw that vector very well. It's kind of bothering me there. It's a little tilted, isn't it? Okay, let me see if I can do a slightly better job. All right, so only slightly better, but still. Okay, so that's the idea. Now let me give you a hint here too. Let's just pretend like for a minute this vector has length 5. Okay, well how would I get that length down to 1? I would divide by 5, right? Now there's one small thing, it's mostly just with vocabulary. Notice we've only talked about scalar multiple as an operation. We haven't talked about dividing, all right? But how do you get around that? Dividing by 5 is the same as multiplying by 1/5, okay? So this vector right here would just be a scalar multiple of v because it's in the same direction, and it would just be 1/5 v, okay? Like that. And now since that's the length of v, in general what we'll need to do is take the length of v and do 1 over the length of v to get this unit vector. Now we want some standard notation for this vector right here. Okay, and so what we'll do is we'll use this notation. Notice this is a vector, and we'll use the letter E, and then we'll subscript it with whatever vector we're trying to find the unit vector from. So what this notation will mean is it's the unit vector in the same direction as v. Okay, sometimes we want the unit vector in the opposite direction as v. Okay, and so think about how do we reverse direction? We just multiply by -1. Okay, and so just keep that in mind. I'm sure you'll see some problems that have to do with that. All right, so make sure you realize too that you know, if I had labeled this thing W instead or U instead, then we would put U or W right here. Okay, so this subscript is whatever vector we're talking about. Now, if you think about what we just said about how we find this, what do? We take our vector V because we want to be in the same direction, but then we multiply by 1 over its length, like that. Okay, be careful. And what you want to start doing as we start doing more sophisticated things is think about whenever you're finding a vector and whenever you're finding a scalar, and make sure you realize this is a vector because I have a scalar times a vector, so that's a scalar multiple of the vector. Okay, so just to see this in action here, and so say I have the vector v equal to 3, 5. Okay, like that. So if we go and find the length of that vector, that's going to be the square root of 9 plus 25, which is the square root of 34. Square root of 34 doesn't simplify anymore, so we would just leave it as the square root of 34. Okay, and so if I wanted the unit vector in the direction of v, that would be e sub v. Okay, and so I do 1 over the square root of 34 times 3, 5. Sometimes we leave it in that form, sometimes we distribute in. You'd probably distribute in and then rationalize. You might want to pause and make sure you can get this. But if you did that, it would be 3 square root of 34 over 34, comma, 5 square root of 34 over 34. Okay, it just depends on what you're doing. I don't always, especially in more advanced classes, I don't always insist that people rationalize, so often I'll leave it like that. Okay, by the way, too, just to point this out, if you were to need the vector in the opposite direction of v, but the unit vector in the opposite direction of v, all you do is change the signs on the inside here to reverse the direction. Okay, here's a good question. After you absorb it, you might want to pause it and see if you can think about how you would answer this. Okay, so say I'm given this vector v, 6, -2. Okay, and I want to find the vector in the opposite direction of v of length 5. Okay, so maybe pause and see if you can think about how you do that. I'm going to go ahead and go on though. All right, so the key thing is here is I can find the vector in the opposite direction of v, the vector in the opposite direction of v. I can find the unit vector, but I'm already written it this way, of length 1. We just talked about how to do that. Okay, so opposite direction, I just take the -1 times, and then I find this unit vector in the same direction as v. Okay, so that's going to be -1 over the length of v. Notice I just changed my notation. I've been using the single bar there, but anyway, times the vector v. Okay, so we need the length of v. That's going to be the square root of 36 plus 4. Okay, squaring each component and adding them together. That's the square root of 40, which simplifies to 2 square roots of 10. All right, so that's the length of v. So to get this negative e sub v, I have negative 1 over 2 root 10 times the vector 6, -2. Now, like I said on the last slide, we not necessarily want to distribute this in. Why would I claim we want to distribute this 1/2 in? Because these are both even numbers. Okay, and let's go ahead and distribute the negative as well at the same time. So we have 1 over the square root of 10, and then we would have -3, +1. Okay, so now you've got to be careful. We're not done yet. This is the unit vector with the opposite direction. Okay, and so unit vector means that its length is equal to 1. Okay, but why am I saying we're not done? We want the length equal to 5. Okay, so what would we do? If this thing has length 1, I would just need to multiply it times 5 to stretch out its length. Okay, and so I'll just call it W for the vector we want. Okay, I would just do multiply this vector by 5, so I get 5 over the square root of 10 times negative 3 comma 1. And if you wanted to, you could distribute everything in. You could leave the square root out front. You might, depending on who's watching this, it might depend on what your instructor tells you to do. Okay, so, but to me, that's fine right there. So that's just kind of combining all the stuff we've been talking about in the last few slides. Okay, so what we want to talk about now are what are called the standard basis vectors. And these are important in and of themselves. But once we get these down, it leads to an alternate notation for vectors that especially engineers use more than the angle bracket notation. Okay, we got to be careful of that. All right, so anyway, the standard basis vectors, when we're in 2 dimensions, okay, we'll get another one whenever we go to 3 dimensions, okay, but the standard basis vectors are the letter I and the letter J, okay, and so the vector I is just the vector 1, 0, and the vector J is just the vector 0, 1, so they're very basic. Now, sometimes, especially in more abstract treatments, this vector is called E1 and this vector is called E2. I won't really get into that. I'm just warning you if you do some other reading, or you may have or will see that notation in some other classes. Okay, so, just in terms of picture-wise, if I draw the axis, I'm going to do it in white just so we can see them better. But, if here's one on the x-axis and here's the one on the y-axis, then right here is I, right here is J, and then just, since we're here, make sure you realize too, the vector going here 1 unit is negative I, and the vector going here is negative J. Okay, so they're very basic vectors. They don't really seem like a whole lot, but here's the key thing, especially about the alternate notation, is what we can do is we can write any vector in terms of I and J. So let's take the vector 3, 5 right now. Okay, well, if you think about it, I can think about that vector as being the sum of the vector 3, 0 and the vector 0, 5. Okay, now once I've broken those out, because of those zeros, in the first vector I can factor out a 3. So I get 3 times the vector 1, 0. Okay, and then in the second vector I can factor out the 5 and I get the vector 0, 1. Okay, why is that relevant? Because I've written that vector as 3i plus 5j. Okay, like that. And so that's why, like I say, especially engineers, but people in other fields too, and some people just like the notation better. Okay, so one way to denote vectors is with the angle brackets and given the x, y coordinates. And another way is to use this notation, the ij notation. Okay, and so in general, if you have a vector v1, v2, you could equivalently write that as, I started to use the same example, v1i plus v2j. Okay, like that. So that's kind of up to you. Again, you typically want to answer problems in the format that they come, though, so be aware of that too. One small advantage to this notation is, imagine having the vector like 0, 5. Okay, you can just save a little bit of notation since right here you would have 0 times I, and 0 times anything is 0. You could just simply write that vector as 5j. You don't have to include the I part. You could say 0i plus 5j, but you wouldn't have to. Now, one other thing too, this is a little bit abstract, but whenever you take a vector, when you take a vector and you write it as some scalar times one vector plus another scalar times another vector, that thing, right, that kind of form, it ends up being important in more deeper treatments of math and vectors, but this is called a linear combination of those vectors. Okay, it's not terribly important, but you'll probably see that vocabulary either in reading or in other classes, or even ideally you would be seeing it because you're using it. And just to make sure you see this, say you have a problem where you have these two vectors, 5i minus 3j, and then you need to add it to 2i plus 7j. Okay, like that. Now make sure first of all, make sure you realize this is just like saying the vector 5, negative 3 plus 2, 7, like that. And remember, we add component by component. So I would add the 5 and the 2, and then I would add the negative 3 and the 7 as the y coordinate. Okay, but usually we kind of think about collecting like terms right here, and so we have these two I terms, and so we typically we wouldn't write it this explicitly, we would just do it, but that's an I. But I'm just regrouping the I terms, and then I'm regrouping the J terms like that. Okay, and so there I would have 7i plus 4j. Alright, so nothing really to overthink right there. It's just the i's kind of acting like the x coordinate, and the j's acting like the y coordinate. Let's denote that as an example, and there's our answer. Okay, and then you could see some of those simplified forms like I mentioned. So I could have something like negative 3i plus 6j, and then just be adding it to 3j, or here, yeah, well, let's just do 3j. Okay, like that. And so there I would, there's no other I term to group it with, so this would just be negative 3i. All right, and then I would do 6 plus 3, so then that would be 9j. Okay, the example I started to do too is say I had this same vector 3i plus 6j, but then I subtracted 6j from it. Okay, and so there we would get negative 3i plus 0j, like that, but we don't necessarily have to write that 0 term, so most people would just write that as negative 3i as the answer. Okay, that should do it for this video. So we're getting the basics down. Now, as we start getting comfortable with it, what we're going to start doing is introducing three-dimensional coordinates and talk about the geometry in there and how to deal with vectors in there. And then we'll progress to the different kinds of products in vector arithmetic. There's actually two that do very different things for us. All right, I hope that helps, and I wish you the best.